Hello everybody, and welcome to Calculus Review for the Exam 3. So let me start by making sure we know what we're supposed to study. So we start in section 3.10, and in that section, we only covered linearization and linear approximation. We didn't cover the differentials, so just keep that in mind. So page 254 and page 255, and the top of page 256, that's basically what we covered. So you should definitely memorize the linearization formula right here, page 254, and that once you do the approximation, that the function is approximately the linearization when x is near a. Okay, so that's the basic formulas you need for linear approximation, and of course we'll go over one or two of the problems tonight. All right. Next, we jump to chapter 4, which is maximum and minimum values. That's page 280. You should know what absolute max and mins are. Local max and mins, that's page 280, as I said. You should just briefly read over the extreme value theorem. That's telling us that every continuous function on a closed interval has a max and a min. So that's on page 281. You should understand Fermat's theorem, that a function that has a local max or min at a number c, and if the derivative exists, then the derivative has to be 0 there, like figure 11. All right. You should understand what a critical number is. Page 284, either the derivative is 0 or the derivative does not exist. All right, closed interval method, that's an important one. It's on page 284. You should definitely know how to do the closed interval method, and try not to confuse it with some of the other derivative tests. Okay. Next, we skipped 4.2 and we go to 4.3, derivative and graphing. So you should know the increasing decreasing test, page 297. These are all in the notes, by the way. The notes come directly from the book. You should know the first derivative test, page 298. And look at the nice pictures here on the bottom of page 298. You should know what the second derivative says about the function. So I would look at the 4 pictures on the bottom of page 299 and the top of page 300. They show you the different possibilities of concave up and down and increasing, decreasing. Try not to confuse concave up and down with increasing, decreasing. So you should know what concavity is, page 300. And the concavity test on the bottom of page 300. Make sure you memorize that. And you should definitely know what an inflection point is, page 301. Second derivative test, just be familiar with that. You don't have to memorize it, but it's useful. All right, curve sketching. So make sure you can graph functions using calculus. We'll try to go over an example tonight. All right. L'Hopital's rule. So L'Hopital's rule, basically, you should make sure you always test that you could use L'Hopital's rule. That's page 310 on the bottom. The fraction has to be of type 0 over 0 or infinity over infinity. So once you verify that, then you're good and you can use L'Hopital's rule. So there's a few examples on page 311, 312. Like example 1, 2, and 3, we did those in class. Look at example 5 on the top of page 313. That's a fake L'Hopital rule problem. And then there are other types of indeterminate forms. So the only other one you need to study is 0 times infinity. There are many others, but for test 3, you can stick with the 0 times infinity. So like something like example 6, bottom of page 313. And some of the other examples. Like for this test, you could skip like 0 to the 0, infinity to the 0, and 1 to the infinity. All right, then we jump to optimization. So for optimization, it's probably useful to study the steps in solving these problems. Page 336. There's a nice step-by-step approach here. Tells you how to do it. And then go over the review problems that I mentioned in optimization. We'll try to do one tonight. Okay. Next, we jump to 4.9, which is antiderivatives. And for antiderivatives, we pretty much covered the section, but it's not a big section. You do have to be careful that you don't confuse them with derivatives. So page 357, understand what an antiderivative is. And you should memorize this table on page 358. You should know the antiderivative formulas. And basically be able to do the problems like we did in class, which are example 2, 3, and 4. We basically did those. We did a problem like example 6 also, page 360. All right, that's what you need to study for the test. All right, so now let's try to do some problems. So let's start with, I'll aim to do one question from each section, but we'll see how time goes. But let's see what we could do. All right, how about 3.10, number 1, 3, 5, or 7? Let's see. 1, 3, 5, or 7. Why don't we try number 3? That's a pretty standard one, something like what we did in class. All right. So f of x is the cube root function. So all right, this is 3.10. 3.10. Number. This pen is not cooperating. Okay, number 3. So f of x is x to the 1/3 power. A is equal to 8. And find L of x, find the linearization, and approximate the cube root of 8.2. So this is a pretty standard problem. All right, so f prime of x, we need the derivative for sure, 1/3 x to the negative 2/3. All right, so we need f of a. F of a would be 8 to the 1/3 power, which is 2. And we need f prime of a, which is 1/3 8 to the negative 2/3 power, which is 1/12. So the linearization, L of x, is equal to f of a, 2, plus f prime of a, 1/12, times x minus a. A is 8, right? All right, so we got the formula, and f of a plus f prime of a times x minus a. So the idea is that this is approximately equal to x to the 1/3 power, which is the cube root. As long as x is approximately 8. 8.2 is approximately 8, so let's just plug in 8.2 into both sides and say that the cube root of 8.2 approximately equal to 2 plus 1/12 times 8.2 minus 8. We plug in this into the calculator. We get 2 plus 1, 2 plus 1 over 12 times 8.2 minus 8 is 0.2. 2.01. 7. And that's the answer. All right, next. Let's go to 4.1, max min values. 4.1. All right. 23, 27. Those are too easy. I'll skip those. You guys can figure those out from the solutions. 29, 33. All right, critical numbers. Let me see if I can get to the... See, I could do a critical number problem, but I might as well do one that includes some other things. Like, how about 51? Yeah, let's try 51. So, 4.1, number 51. This one is a basic closed interval method problem, and it includes critical numbers. All right, so f of x equals 12 plus 4x minus x squared on the interval 0 to 5, and the goal is to find the absolute max and min. Okay, so let's find the critical number first. So f prime of x equals, set it equal to 0. So taking the derivative, we get 4 minus 2x. So x is 2. Okay, so we set up our t-chart. We put the critical number, and then we put the endpoints. Now, since we want the max and min value, we go to the original function. So f of x. All right, so let's plug in. So let's see. 12 plus 8 is 20, minus 4, 16. If you plug in 0, we get 12. If we plug in 5, 12 plus 20 is 32, minus 25, 7. All right, so 7 is the absolute min, and 2 is the absolute max. So 2 comma 16, 5 comma 7. So there's your absolute max and your absolute min. So notice that we plug this into the original function to get the y values. Try not to confuse that. Try not to confuse that with some of the other tests where you go into the derivative to find the number line of like the derivative. All right, let's see. 4.3. So for section 4.3, that's basically graphing. So why don't we try one of the basic graphing problems? How about number like 57, 59, 45. Let's try 45. I'm trying to demonstrate more of like the simpler ones, so this way that at least you could see the methods, clearly. But don't forget, you need to practice all of the ones that I indicated. I don't have time to do 10 complicated examples. It would take a long time, but you really need to practice that to get good at it. All right, so let's try number on 4.3, number 45. All right, so f of x is x cubed minus 3x squared plus 4. All right, increase and decrease. So we want to basically figure out as much as we can about the function using calculus. First derivative, second derivative test. All right, let's start with the critical numbers. All right, so f prime of x is equal to 3x squared minus 6x. Set it equal to 0. And solve for the critical numbers. X, well, let's factor it. So factoring it a little more. So take out a 3x and we get x minus 2 equals 0. So x is 0 and x is 2. All right, number line for f prime. So we're going to plug into the first derivative we're going to plug in the first derivative in order to figure out when the first derivative is positive and when the first derivative is negative. All right, so if we plug in -1, negative times a negative, that's a positive. If we plug in 1, that'll be negative. If we plug in 3, positive, positive. Okay, so the conclusion is that the function increases from -infinity to 0. So we increase -infinity to 0 and from 2 to infinity. And we decrease from 0 to 2. Since we're going from positive to negative, it's going up and then down, and then it goes down and then up. So we have a local max when x is 0, local min, x is 2. All right. Next, concavity. So let's calculate the second derivative. So start from there again, and we get 6x minus 6 Set it equals 0 so we can form the number line. Factor out the 6, x minus 1 equals 0, so x is 1. Alright, so we have the number line for f double prime, and on it just put 1. Okay, when x is less than 1, like 0, you'll get negative. And when x is bigger than 1, you'll get positives. So we're concave up from 1 to infinity, and concave down from negative infinity to 1. And it does change concavity at 1, so x equals 1, point of inflection. Okay. Sketch the graph. So we can now basically come up with a decent graph. Since this is x to the third power, we know the long-term behavior is something like this. But it's going to have turning points. So, but in the end, it's going to look like this when x goes to infinity and minus infinity. So let's see. So we're going to be concave down but increasing. And then we're going to have a local maximum. And then we're going to have a local minimum. And then we're going to go up. So let's see. When x is, where did these occur? We have a local max at 0, right? So let's figure out the y value. 0, go to the original function, 4. Now we have a minimum at 2. So let's see, when x is 2, what's the y value? 8 minus 12, negative 4 plus 4 is 0. So that's actually the x-axis. And we do have a point of inflection at x equals 1. So it's somewhere between the two. That's where it should be approximately. When x is 1, 1 minus 3 is negative 2, plus 4 is 2. So that would be the point 1, 2. And basically, that's your graph. Okay? If, for example, at a critical number, if it did not change sign, then the graph would have been like the x cubed graph, see? But this is not the case in our case. But this is a possibility if it looks like this. Let's say it looks like positive